240 miles above Earth's surface, a massive structure floats in orbit, circling the planet at more than 28,000 kilometers per hour, a place never meant for human life, where there is almost no air, where temperatures swing from negative 157 degrees Celsius to more than plus 120 degrees Celsius every 45 minutes, and where sunlight hits with the full force of space, unfiltered, harsh, and relentless. And yet, here, in one of the harshest environments imaginable, humans live, work, and explore. This is not just a spacecraft, and it's not just a satellite. This is the International Space Station ISS, one of the most complex engineering projects ever attempted, built piece by piece outside Earth. A symbol of collaboration, science, and human ambition. So the question becomes, how does it work? And what makes it unlike anything humanity has ever built? To understand the scale of the ISS, we first have to understand where it lives. The station orbits within what's called low Earth orbit. Up here, gravity still exists around 90% of what we feel on the ground, yet astronauts experience microgravity, a near weightless state where objects float freely. This environment creates opportunities impossible to replicate on Earth: research in biology, fluid physics, new materials, Earth observation, and space medicine. But the ISS isn't just a floating laboratory, it's a multinational achievement involving NASA, United States; Roscosmos, Russia; ESA, Europe; JAXA, Japan; CSA, Canada. Together, these agencies built something no single nation could afford or maintain alone. The total cost of construction and operation has surpassed $150 billion, making it one of the most expensive human-made structures in history. Yet for many scientists and engineers, the ISS is priceless because it represents something far greater than technology. It represents humanity learning how to live beyond Earth. The dream of living in space began decades before the ISS. Back in the 1970 seconds, the Soviet Union launched Salyut 1, the world's first space station. It proved humans could live in orbit longer than a few days, but it was small, unreliable, and limited. Then came Mir, the Soviet and later Russian space station that operated from 1986 to 2001. Mir changed everything. Astronauts stayed for months, ran experiments, assembled new modules, and learned how microgravity affected the human body. But Mir wasn't perfect. It faced fires, limited power, air quality problems, and even a collision with the Progress spacecraft in 1997. These events demonstrated the risks of long-duration spaceflight and exposed the fragility of early station designs. Meanwhile, NASA was developing Space Station Freedom, a large U.S.-led orbital station planned during the 1980 seconds. But the project was too costly, too ambitious, and eventually stalled. And then a realization emerged. No single nation had the resources, budget, or technology to build a fully sustainable station alone. So, instead of competing, the world decided to collaborate. Former rivals of the Cold War sat at the same table and drafted a new vision. A station built not by one country but by many. A station intended not only for research but for the future of humanity. In 1998, the first ISS module, Zarya, was launched into space. And with that launch, a new era began, not of conflict, but of cooperation. The ISS wasn't launched in one piece. Instead, it was assembled in orbit, like a giant construction project floating in space. Over more than a decade, more than 150 spacecraft deliveries helped build and extend it using U.S. space shuttles, Russian Soyuz and Progress vehicles, and automated resupply craft from Europe, Japan, and later private companies. Each new piece was added through a carefully choreographed sequence of robotic movement and astronaut spacewalks. At completion, the ISS reached 109 meters in length, more than 420 metric tons, with internal space comparable to the cabin of a Boeing 747, and although enormous, it travels incredibly fast, making one full orbit every 90 minutes, meaning astronauts witness 16 sunrises and 16 sunsets every single day. Yet none of this would matter if the ISS couldn't keep its crew alive. To do that, the engineers behind the station designed systems that function flawlessly in an environment where failure is not an inconvenience, but a threat to life. Energy, water, oxygen, orbit control, robotics, maintenance. Together, these systems transform the ISS from a metal structure into a fully functioning home. The ISS is built as a modular system, meaning it can expand, evolve, and be repaired over time. More than 16 major pressurized modules make up the core of the station. Each one has a purpose. Zvezda and Zarya, propulsion, navigation, life support. Destiny Lab, United States Scientific Research Hub. Kibo, Japan, includes an external experiment platform. Columbus, biological and environmental research. Unity and Harmony, connection hubs and system dister. Each module maintains internal air pressure similar to a commercial aircraft. The station's shell is made of layered aluminum alloys and Kevlar micrometeoroid shielding, protecting against tiny space particles traveling faster than bullets. Inside, every inch of volume is used. It's a three-dimensional workspace where floors, ceilings, and walls no longer exist. The station functions not like a building, but like a floating ecosystem for science. Energy is the lifeline of the ISS. With no power cables connecting it to Earth, the station relies entirely on sunlight. Its enormous solar arrays cover more than 2,500 square meters, generating up to 120 kilowatts of electricity, enough to power roughly 50 homes. These panels rotate continuously to face the sun, while lithium-ion batteries store excess power to keep the station running whenever it passes through Earth's shadow. Electricity sustains everything: environmental control, water recycling, air purification, computers, communications, robotics. A constant balance of power is required. Too little energy, and systems shut down. Too much, and electronics overheat. Engineers describe it as keeping a city alive on a battery forever. Water is one of the most valuable resources aboard the ISS. Since launching water from Earth costs up to $10,000 per liter, the station must recycle nearly everything. Sweat, humidity, condensation, even urine, all of it is captured, filtered, and purified into clean drinking water. The system is so efficient that astronauts joke, yesterday's coffee becomes tomorrow's coffee. Air is also recycled. Carbon dioxide is removed, and oxygen is supplied through electrolysis, splitting water molecules into hydrogen and oxygen. Backup chemical oxygen generators exist in case of system failure, and yes, they have been used. The ultimate goal is sustainability, a closed-loop system where nothing is wasted. It's a prototype not just for living in orbit, but for future bases on the Moon and Mars. Despite orbiting at extreme speed, the ISS doesn't stay at the same altitude forever. Earth's thin upper atmosphere creates drag. Gradually, the station falls. To prevent this, visiting spacecraft such as Progress or Cygnus fire their thrusters to push the ISS back into higher orbit. This maneuver, called a reboost, must be calculated with extraordinary precision. Inside Mission Control, dozens of specialists monitor its orbital path constantly, ensuring collision avoidance with debris. alignment for spacecraft docking, stability for experiments needing microgravity. Operating the ISS is less like flying a spacecraft and more like managing a floating city. 5.5. Robotics and EVA maintenance to 230 words. Some engineering challenges are too dangerous or too complex for humans alone. That's where robotics come in. The ISS features Canadarm2, a 17-meter robotic arm used for assembly and cargo capture. Dextra, a precision robotic tool for delicate tasks. SPDM systems, performing maintenance remotely. But even with robots, many repairs still require astronauts to exit the station. These operations are called EVA, extravehicular activities, commonly known as spacewalks. A single EVA lasts 6 to 8 hours, conducted in a vacuum, with astronauts wearing technologically advanced spacesuits, serving as personal spacecraft. A micrometeoroid, the size of a grain of sand, could puncture a suit. One mistake could be fatal. Yet EVA missions remain essential because space constantly tries to damage the ISS. And humans constantly push back. Living in microgravity isn't just strange, it transforms the human body. Within weeks, muscles weaken, bones lose density, body fluids shift toward the head, faces swell, legs thin out. Some astronauts experience vision changes from pressure on their eyes. To slow this process, every crew member must exercise at least 2 hours per day using resistance machines, treadmills, and stationary bikes. Sleep also becomes unusual. There is no up or down. Astronauts sleep floating upright in sleeping bags attached to the wall. But with challenges come moments no one else on Earth can experience. Inside the observation cupola, astronauts watch lightning storms racing across continents, city lights outlining borders invisible from space, auroras swirling like green fire across the dark Earth. Up here, the world is no longer divided by countries or politics.
We are
It looks
truly
like
honored
one
to
home.
be here,
The
representing our
ISS
nations
is
together.
not the final goal, it's a stepping
It's a testament to what we
It
can
teaches
achieve.
us how to live in space long-term, how to maintain life support systems, how the body adapts, and how technology evolves. Everything we learn here will shape future missions. The Lunar Gateway,
Everything looks good from up
orbiting the
here.
moon,
Thumbs up indeed,
permanent
Commander.
moon bases, and eventually,
We'll see you at the next module.
human settlement on Mars. The ISS answers a question once thought impossible. Can humans truly live beyond Earth? So far, the answer appears to be yes. And because of this, the ISS is more than a machine. It's a rehearsal for humanity's future. The International Space Station stands as one of humanity's greatest engineering achievements, not because of its size or its cost, but because of what it represents. In a world often divided by borders and beliefs, the ISS proves that when we choose cooperation over competition, we can build something extraordinary. If you look up at the night sky, you might see it a bright dot moving quickly across the darkness, a reminder of what we are capable of. So now, the question comes to you. If you had the chance to live on the ISS for a month, would you go?
The next giant
Tell
leap
us in the
begins
comments.
here.
And as always, thank you
Establishing
for
a
watching.
permanent presence on the
Stay
moon.
curious.